Hello, welcome to Calculus. I'm Quillen, and today we're going to be continuing our discussion of limits. In the last video, we talked about one-sided limits. Today, we're going to do a little bit of a pivot and talk about a special case of the regular standard limit, the one that we first talked about. So if you'll remember, I said that this n had to equal some real number. And again, this is not super rigorous, correct notation, but this is sufficient for understanding. However, I also said that there are two special cases where n does not equal a real number, and that is where n equals positive or negative infinity. And if you start thinking about the idea of a limit, the x value getting closer and closer to positive or negative infinity, you might recall back to Algebra 1 or maybe Algebra 2, depending on where you're from, the idea of end behavior. End behavior, if you'll recall, is what a graph does as you take it to its extremes. So that was written something like this: x to infinity, sometimes you'd have negative infinity, comma, y to some value. Let's call that value u. So what this describes is if you go to look at the endpoints of the graph, of course you can't truly do that because the graph won't have endpoints. But if you were to find the endpoints of the graph, you would find what the point notation of that is. So your Cartesian coordinates. And this is very, very similar to the idea of a limit. So mathematicians have sort of co-opted them, grafted them together into unbounded limits, the idea of an unbounded limit. So just like you would expect, say you want to find the limit as x goes to infinity of some function, you just write the limit as x goes to infinity of your function f. And it's the exact same notation. Similarly, if you want to find the limit as x goes to negative infinity, you just add a negative sign, but you do want to do it in front of the infinity symbol instead of behind it, so that it cannot be confused for a left-handed limit or a right-handed limit. Now, like I said, this does smell like end behavior, and so this will probably, hopefully, come very naturally to you, meaning that not a whole lot of effort will be required in learning it. However, if you do need some more help, then you can watch these videos a couple times to see where all the little notes are for the nuances. All right, I have moved over to Desmos and gone ahead and typed in some functions. We're going to talk about the unbounded limits of each of these functions and sort of how you can feel like you naturally understand what the unbounded limits are describing. So this first function should be very familiar. F of x equals x is just the most basic linear parent equation. Let's talk about its unbounded limits. So first, what is the limit as x approaches positive infinity of x? Well, as x goes to infinity, x is going to go to infinity. So you can trace up this and it'll keep going forever and ever and ever until it gets to positive infinity, but it will not get to positive infinity until it gets to x equals positive infinity. Same is true if you go backwards. As x approaches negative infinity, x is going to go to negative infinity. So, as x approaches negative infinity going this direction, f of x, which is just equal to x, is also going to go to negative infinity. It's going to go down and down and down forever. And when it finally gets to negative infinity, you can think about it as being at f of x, or y, equals negative infinity. Let's now think about g of x equaling x squared. Something you'll notice about this is it's a parabola, and parabolas, both of their ends go towards the same y direction. They both go either positive or negative. This one goes positive because it's the parent equation. So as x goes to infinity, the limit as x approaches infinity is going to be infinity again, because if you take a graph and you look at it, you take this graph rather, and you look at it stretching up towards infinity this way in the horizontal direction, it's of course also going to get there stretching that same direction in the positive y direction. Now, what about the negative direction? What is the limit as x approaches negative infinity of x squared? Well, tracing this line going as far horizontally as we can, it's going to go up and up and up forever. So, in some cases, both unbounded limits will be the same direction. And it makes sense that they could be infinite values, so that's fairly logical. Next, let's look at h of x equals sine of x. So the main characteristic of the function sine of x is that it oscillates. It goes up and down and up and down and up and down with complete regularity forever. You can do things to make it not regular, but the parent function is completely regular, completely recurring, and oscillating. So then, what does it approach as x goes to infinity? If we went all the way in this direction forever, what would it look like we were getting close to? Well, we can't really say. We don't know if when we get to positive infinity, we're going to be at a crest or a trough or right in the middle on the axis. And because we do not know what it's going to approach, we cannot define the limit. Therefore, the limit as x approaches positive infinity of sine of x equals, rather, it does not exist. It does not equal anything. So if you wanted to find the limit as x approaches infinity of this right here, you would write d in e. Maybe that's legible enough. The same is true if you go in the negative direction. It's still oscillating completely infinitely if you go in the negative direction. We don't know what it's going to approach. And because we don't know what it's going to approach, and we don't know because it's not approaching anything in particular. Because that's true, the unbounded limit negative direction, as x approaches negative infinity, that is also d and e. It also does not exist. A very important note about d and e, limits that don't exist. Limits that don't exist are not equal to d and e. If you were asked to find a limit and your finding is that it doesn't exist, you simply write d and e and circle it or put a box around it on your homework. You do not have lim of something equals d and e because d and e is not a value. Now, let's look at m of x equals e to the x. And the reason I skip so many values in here is because they have other meanings. So you don't nominally use them for defining functions, but you can. I just didn't here. So first, let's talk about the positive unbounded limit. So as x goes to infinity, as we go along this horizontal axis forever, tracing and finding up to the graph, it's still going to go to infinity. So thinking about that, if we went forever and ever this way, we would never get to the end, but we would also never get to any stopping point horizontally. So the limit as x approaches infinity of e to the x is infinity, just like for f of x equals x and for g of x equals x squared. But for e to the x, as we approach negative infinity, we do approach a value. We can see that we're approaching a value right here, but that value is a real number. It's 0. That means that the limit, and I'm going to write this down because sometimes this is a little bit difficult for people to comprehend, and seeing it in notation can help. So the limit as x goes to negative infinity, and this pen's a little big, so it's going to be ugly, of e to the x equals, and now let's look at the graph, see what it equals. Well, if we go in this negative direction forever, what value does it look like we're going to get to? That's 0. We're asymptoting at 0. So that means that it equals 0. And that is a general rule that you can apply. If something asymptotes in a direction, then the value of the limit unbounded in that direction is equal to the asymptote if it is a horizontal asymptote. So let me go back, say that again a little bit clearer, hopefully. If something has a horizontal asymptote, then the unbounded limit in that direction of that function is equal to the y value at which it horizontally asymptotes. If that is unclear, then try and just think back to this example and your brain will remember what it means. So I hope that you have found this video helpful, and I hope that you continue to join me on this journey through calculus. This is Quillen signing off.